We are working on page 15, and take notes while you watch this video. We have seen already many equations for power. It's energy over time, but whether you let the numerator be work, or the energy exchanged, or the heat energy, it just depends on the context. We will be focusing on this scenario. We've already seen the situation down below. You have some substance, you're heating it at constant power, so constant power, and the mass inside, the mass of the sample, is also constant. So you're holding it over a flame, perhaps. Maybe it's some ice cubes. They start out really cold, and you heat them at constant power. It starts in the solid phase, moves to the liquid phase, and ends in the gaseous phase. In each phase, there's a portion of time when the temperature is rising. The graph is climbing up the temperature axis, rising up the temperature axis. And in between the phases, you melt here, and then you boil or vaporize here. And the question I want to ask is, what does the steepness of these sections tell us? Here's specifically what we're going to look at. And you can make your guess. Which line indicates higher specific heat capacity? The red or the purple? I'm going to go ahead and give you the answer. Red has a higher specific heat capacity. Maybe this is intuitive, maybe not. Let's understand the reason. We are going to start out by looking at the slope of this graph. Every slope is change in y-axis divided by change in x. The y-axis here is temperature, the x-axis is time. Let's put that aside for the moment. The power equation above is heat over change in time. But of course, heat comes and has one of two effects. It can either increase the temperature, or it can change the phase. Which one is relevant here? The portion is not flat, so temperature is rising. So this equation now becomes mc, change in temperature, divided by the time that passed. Wait a second, that's the slope. So now we could write down power is mass times c times slope. But if power is constant and mass is constant, then their product is a constant. C is inversely proportional then to slope. And that's why the red line, steeper, means less specific heat. That makes sense intuitively. Whoops. Because specific heat is the heat energy needed to raise 1 kilogram by 1 Kelvin, or 1 degree Celsius. Look at the red graph. See how quickly it jumps up when you add heat? That means that the temperature raises 1 degree for the same mass with a very small amount of heat, so it has a lower specific heat. Purple requires more time, and thus it takes more heat to raise the same mass by the same change in temperature. That gives it a higher value of C. The next thing we're going to look at are the flat portions. This is maybe 5 kilograms, perhaps. I'm just making numbers up. And this is the same 5 kilograms. Why would it take more time to boil than vaporize? Why is this second line longer? In fact, that's often the case in many, well, not all, but many situations. Whoops. In many situations, the heat needed to vaporize is often bigger than the heat needed to melt. And as a consequence, the latent heat of vaporization is often bigger. Not always, but sometimes bigger than latent heat of fusion. A longer line, flat portion that is, a longer flat line, indicates more heat needed and a higher a higher latent heat. And again, the reason is, if you need more heat per unit of mass, you have a higher latent heat value. So the question for you that I'm going to have you ponder, why would this be the case? Why would more heat be needed when you were boiling than when you were melting? Ponder that question. Think about the phase change and what's happening. Think about where that heat is going when you add it, and see if you can come up with an answer. Thanks for watching this video.